Section 4.5 deals with the dimension of a vector space. The dimension is simply the number of vectors and a basis for a vector space. A vector space can either be finite dimensional, meaning that it has a finite number of vectors in its basis, or it can be infinite dimensional. And we'll look in a moment at some different dimensions of different vector spaces to see what finite and infinite mean. Some examples of some finite dimensional vector spaces include things like R3. In this case, if we look at the standard basis for R3, you'll notice that it contains 3 vectors. So we know that the dimension for this vector space is 3. If you look at Rn, notice that the standard basis contains n vectors, so its dimension is n. And if we look at Pn, if you remember, Pn is isomorphic to Rn plus 1. For example, P2 is isomorphic to R3. So this has n plus 1 vectors in the basis, so its dimension is n plus 1. Some examples of infinite dimensional spaces include things like, this is script f of r, that is functions that contain a real domain and range. So this is functions with real values for the domain and the range. In that case, there are infinitely many such functions, so there is no finite number of elements in the basis, so it's infinite dimensional. You could also have something like all real continuous functions or all real differentiable functions. All of those would be examples of infinite dimensional vector spaces. So one thing that's nice to know is if you have an n-dimensional vector space, then any basis for that vector space, let's call it V, has only n vectors. It won't have any more or any less. So let's look at the following theorem. It says if V has a basis, B, with B1 to Bn as its elements, then any set in V containing more than n vectors must be a linearly dependent set. Let's consider this set S that we have here with these 2 vectors. It turns out that the set S is a basis for R2. If I add another vector to S, say for example this vector 3, 7, notice that S is no longer a basis. In fact, the set is linearly dependent. Well, how do we know that? We know that because we have 3 vectors in R2, which makes a linear system for this set, makes it underdetermined, right? So anytime I add in a new vector to a basis, I end up forming a linearly dependent set. The second theorem says what we already said, and that's if I have any basis for V, and it is n-dimensional, that basis must have n elements. In this example, we're going to find the dimension and basis for the subspace that we have here. So this subspace is the span of these 3 vectors, 1, 1, 1, 2, 1, negative 1, and 1, 0, negative 2. So we know that just means it's all the vectors that are linear combinations of these 3 vectors. So we're going to start this problem by first finding a basis for this subspace. So we need to find whether or not this set of vectors is linearly independent. We know that it spans the subspace, but are they linearly independent? Notice that when I take these vectors and place them in a matrix and put that matrix in row echelon form, we see that there are 2 pivot columns. The fact that we have 2 pivot columns means that we have one non-pivot column, which tells us that AX equal to 0 is going to have non-trivial solutions. So this is a linearly dependent set. So we need to remove the vector that corresponds to the last column. So we need to remove this vector right here, and the remaining vectors will form a basis. So here we have our basis for the subspace. These vectors span the subspace and they are linearly independent. That's what makes them a basis. And so we can say that the dimension for this subspace is equal to 2. All right, so the dimension for S is equal to 2 because the number of vectors in the subspace are 2 vectors, and the basis for the subspace are 2. Let's look at the following subspace. This is a subspace H, and notice that it has quantities A and B within it. And A and B, in this case, can take on any real numbers. So there are infinitely many vectors in this subspace. I've taken this subspace and now written it in parametric form. So the two vectors 1, 1, 0 and negative 2, 1, 3 span the subspace H, right? Because it's just all possible linear combinations of those two vectors. So to make sure that it's a basis for the subspace, we also need to know that they are linearly independent. And we have that immediately, right? Because we have two vectors, and we see that these are not scalar multiples of each other, which implies that they are linearly independent. Hence, a basis for H would simply be the two vectors 1, 1, 0 and negative 2, 1, 3. And then we would say that the dimension of H, in this case, is also equal to 2. I would like you to follow along and do this following example with me. So here we have a subspace H, and we would like to find a basis for H. So the first thing I want you to do is to write H in parametric form. You should pause the video at this time to complete the problem. When you write H in parametric form, you end up with the following set of vectors, and this set of vectors will span the subspace H. The problem is that we know that this set is not a linearly independent set because we have 4 vectors that are in R3, which tells us that it's an underdetermined linear system. Hence, to find a basis, we know that we have to eliminate one of these vectors. At this point, I want you to write these vectors in a matrix and perform row operations to find out which of the columns from S must be eliminated. So I've placed this matrix into row echelon form, and I'm identifying now 3 pivot columns. So we know that the last column is a non-pivot column, which tells us that we need to eliminate the last vector from S. Hence, a basis for S is going to be given, a basis for H is going to be given by this set of vectors. So now we simply count the number of vectors in the basis, and we find out that the dimension of S is equal to 3. I invite you to consider the subspace that is given on this slide and go through the same process and see if you can find a basis for H as well as the dimension for the basis. If necessary, we'll discuss this problem further in class. In the same way that we can take a set that spans a subspace but is not linearly independent and remove vectors until we get a linearly independent set to form a basis, we can also extend sets to form bases. So we're going to see how that process works. Let's look at this theorem. It says let V be an n-dimensional vector space with a subspace H of V. Any linearly independent set S in H can be expanded to form a basis for H. This just says that I can take any set and expand that set so that it is a basis for H. So we're going to see how that's done. In this case, we have a set of vectors, S, that is in P2, but is not a basis for P2. And we know that it's not a basis for P2 because the dimension of P2 is equal to 3. Now, how do I know that? If we look at the standard basis for P2, it contains the following: 1, x, and x squared. It contains 3 elements, just as the standard basis for R3 contains 3 elements. Hence, S in this case is not a basis, but we're going to extend it to make a basis, and I'll show you how. I've created a new set which I'm calling in this case S tilde, where S tilde is just S, and I've added some stuff to it. And what I've added is simply the standard basis in P2. So notice now we have a lengthier set, and this set does indeed span P2 because I put the standard basis in there. So now what I'm going to do is simply put these vectors into a matrix and eliminate those that make the set linearly dependent, right? This is a linearly independent set because we have more vectors in the set than are needed. So I've taken each of these polynomials and represented them as vectors in R3. And now I've taken the matrix and put it into row echelon form. And notice that the first three elements, 1, 2, 3, are represented as pivot columns. The last two are eliminated because they are non-pivot columns. So the set -1 plus x squared, 3 minus 2x, and 1 form a basis for P2. We're now going to look at this thing called the basis theorem, and it really makes our life quite a bit easier, and I'll try to tell you why. The basis theorem says that if I have some vector space with a dimension that's greater than or equal to 1, and I have some linearly independent set that's in my vector space, and that linearly independent set has p vectors, then automatically I can say that it is a basis for V. So I don't need to show that it spans. So this means if we have a set, for example, of 3 linearly independent vectors in R3, they are automatically a basis for R3. I don't have to show that they span R3. It's given to you automatically. Likewise, if I can show that I have a set of p vectors that spans V, then it's automatically a basis for V. So in this case, I don't have to show that the vectors are linearly independent if they span. Again, the goal is to make sure that I always have p vectors. Remember we said that each vector space, each finite dimensional vector space, will always have n elements. So if I have a set with n elements that's linearly independent, then I know that it spans the vector space. And if I have a set of n elements that span the vector space, then I know that they are automatically linearly independent, and in both cases they form a basis. So in this example, I'm going to put the basis theorem in action. Here I have two vectors in R2. All right, so here's a set of two vectors in R2. We know that they're linearly independent because they're not multiples of each other, and we know if we have two vectors and they're not multiples, then they're linearly independent. So I can automatically say that S is a basis for R2. It is not necessary for me to show that they span R2. Okay, so the fact that they're linearly independent tells me that they're a basis. And I just want to make sure that you understand that by the basis theorem I can say that because I have two vectors in S. Right? And I know that the dimension of R2 is 2. So I have two linearly independent vectors in S, which means that S forms a basis for R2 by the basis theorem. We're now going to talk about the dimension of the null space and the column space of a matrix A, and these are very easy to find. If you remember, when you find the null space, the number of vectors in the null space is equivalent to the number of non-pivot columns, right? So remember, those non-pivot columns identify the free variables, and those free variables are what helps us to create the null space. If I want the dimension of the column space, if you recall, we always look for the pivot columns. So the dimension of column space is always going to be the number of pivot columns of A. And so there is a little theorem that tells us, by the way, the dimension of the column space is also sometimes referred to as the rank of the matrix. So if I take the dimension of the column space, which is the rank, and I add to that the dimension of the null space, that is sometimes referred to as the nullity, then what I'm doing is just adding up the total number of pivot columns with the total number of non-pivot columns. So in the end, what I get is the total number of columns of A. So let's look at the following matrix A, and what we're going to do is find the dimension of the null space, or the nullity of A, and the dimension of the column space, or the rank of A. So all we need to do is take A and put it into row echelon form and identify its pivot columns and its non-pivot columns. So here we have the matrix A in row echelon form. It has 2 pivot columns and 2 non-pivot columns. So the nullity, or the dimension of the null space, is equal to the number of non-pivot columns, which we have here, so that will be 2, and the dimension of the column space is the number of pivot columns, which are also 2. And so that other little theorem tells us that the sum of the nullity, or the number of non-pivot columns, plus the rank, which are the number of pivot columns, should give us the total number of columns in our matrix A.